Welcome back, everybody. In the last video, we ended up going over how to map just a regular screen, just generate pixel addresses for a 1024 by 768 screen. In today's video, we're going to end up using that circuit and using that to map the screen space to the complex plane. So we're going to take the x's and turn them into the reals, and we're going to take the y's and turn them into imaginaries. And it's a really easy process. So the way we do this is we need to realize that our real mapping that we're going to do, since our screen is 1024 by 768, that's a aspect ratio of 4 to 3. So what we need to do is map a distance of 4 in the x to a distance of 3 in the y, and then if we're going to zoom in, we're going to make the y mapping 1.5 and the real mapping 2. And if we zoom in again, then whatever half of 1.5 is, and then half of 2 is obviously 1. So you can see how we're going to zoom in by changing the mapping that we use. So we need to first recognize what the default view is. So our default view is going to be a mapping of -2 to 2, which is a distance of 4. 4 over 1024 is 1 over 256. Imaginary mapping is 1.5 to -1.5, that's a distance of 3. And 3 over 768 is 1 over 256. So I call that the aspect ratio, but that's really the zoom factor that we're going to use. The aspect ratio is more like the screen of 1024 over 768. So it's really just the zoom factor in the x and y direction is the same. So to get the default view, which is, of course, this is our default view, that the first thing we draw, like the moment you turn on the circuit, the moment we build it, will be this frame. This will be the first frame drawn. Anyway, so what we need for that is to know that our real bound is -2. If we're going to start at the negative side, so our real bound is -2 and our imaginary bound is -1.5. Those are two that we're going to care about. And our zoom factor is 1 over 256. So we're going to use the circuit that we made in the last video that actually generates those pixel addresses, and then we're going to use those to map the complex plane using our real bound and our imaginary bound and the zoom factor. So here's an example. Let's say we're just dealing in the x address and the reals. We're on a number line, not a plane, but it's drawn here, the whole thing. But we're just looking on the x-axis, and we're at -2. -2 corresponds to 0 for the x address. Alright, what if you have a 1 x address? Well, how did we even get -2? Well, we took our bound, which was -2, and added 0 over 256 to it. Because it's the 0 address, 0 times the zoom factor, 0 times 256 is 0, plus -2 is -2. So then how do we get the next address? Well, we have to then take the address, which is in the x address would be 1, which would be the next one, multiply it by 256 and add -2 to it, or add -2 plus 1 over 256, I should say. And we keep going like that up until you get to 1 plus 255 over 256. And what that ends up being is -2 plus 1023 over 256. And that's how we end up mapping the complex, or the reals. And then you do the same process for the y's. Instead of starting at a -2, you start at -1.5, and you do the same process, and it'll take the same number of iterations to get to 760. It'll work out the same way to get to 768. And you can see that here. So this is actually the math that we need. So for all x addresses, we're going to take the x times the zoom factor and add the real bound, and then that's the imaginary value. That's the real value. So we're taking x in, and we're outputting the real value for x. Then for y, we're going to take y in, multiply it by the zoom factor, add the imaginary bound, and then y comes in and the imaginary value comes out. So now for each pixel address, we have mapped those values. So now using this, now that we understand what we're going to do, now we're going to build it, and it's really easy. Okay, so before we actually do this mapping, we need to build the multiplier. So if you aren't familiar with fixed point, you should go watch my previous video, which I will link in the description, about how to approach fixed point. And in this video, we're actually going to be using it. So we're going to be using a signed multiplier with 32 bits. We're going to use the first bit, or the most significant bit, as our sign, the 10 bits below that as integers, and the last 21 bits as our fractional bits. So when we multiply two numbers, the output bits double. So if we multiply two 32-bit numbers, we get a 64-bit number output. And we have to truncate that output to the right spot to get back our 32-bit number that has our decimal in the right spot. So when you think about it, if you have this 32-bit number that looks like sine, 10 integers, and then 21 fractional bits, if you double the fractional bits and stick it at the end, you could see that there. And then if you double the integer bits and then put the sign in front, you'll have as many s's there plus the s that's in blue. But then what happens is if we're using a sign multiplier, after where we truncate, it gets sign extended just by the multiplier itself. So we just have a bunch of signs up there and we just truncated it and we just take the sign from there. Because if it's a negative number, it would be all ones below that up to that sign anyway. So you could just truncate it there. It's sign extended basically. So we're going to use that property, and this is how we're going to build our multiplier. So in the next clip, you'll see that. Okay, so here we are in the exact circuit that we left off in. What we're going to do is we're going to go to File, New Embedded Circuit, and we're immediately going to go to File, Save as, Fixed Mult. Cool. So now that we have this fixed mult, we're going to go to our components, arithmetic, multiply, and we're going to do this. Components, I/O. This is going to be one of the easiest circuits we've built. Control C, Control V. Oh, that's what I want to do. And then right click on that, make that 32 bits. Right click on this and make that 32 bits and click this little signed operation box. The output here is now going to be 64 bits. So now we've got to go to components, wires, splitter merger. And we're going to input 64 bits and we're going to output 21 through 52 like that. And now components, output, make that 32 bits and run it, and it works. Okay, so now if we do an example where, here I'll pull up my PyCharm. I'll be right back once this loads. Okay, so I have this little script here, so what I'll do is I'll run it. So we have one sign, 10 integer bits, and 21 fractional ones. Okay, so let's say we want to multiply negative 2.125 there. Okay, and now let's enter another number that we want to multiply. So let's enter, yeah, we'll do another negative. Negative, I don't know, what, 4.60625. We'll make it like that, something dumb. Alright, so now we just take so we just take this, and I'll literally just Control C, and we'll just apply. And then I will Control C and apply. Okay, and now we got this number out, which has which now we have to convert back if we want to know. But anyway, that's how this is working. So we just did that. That is the result of whatever the hell negative 2.125 times negative 4.0625 is, and you can tell because it's not an F or an 8. You know, the most significant bit isn't true in this. It's, you know, a 1, and there's 4. Each hex digit is 4 bits. You know, so like, oh, here's what we could do. Better yet, we'll take the output, put it in decimal, sign decimal. There. Let's do it again. Now if we run it, apply that one. So I got the FFE7 one. We'll grab the other one. Apply, and we get that number out. But of course, that's not going to be a right fixed point format, of course. So it's not really useful. Actually, now that I think about it. Anyway, let's keep moving forward. We want to now save the circuit. And now we're ready to use it in whatever else we need to use. Well, actually, no, we're not. We need to label this A. Label that B. Label that out. Alright, now Control S or file save. I already Control S. Alright, now we're done. So now we're going to exit out of the circuit. We are now going to go to File, new embedded circuit. We're going to call this save as screen map. Okay, and now we're going to go to our components custom and we're going to grab our fixed mult. Just like that. Okay, so now if you remember based on what I said here, what we need to do, we need to take our x times our zoom factor plus our real bound. So let's get that in here. Components, text, okay. Control C, Control V, and we're going to do y times plus the imaginary bound. Alright, so that's what we got to do, written right there in the circuit so we know. So first we're going to we need 2 of these multipliers. And remember that it's in 1.10 plus 21 format, or 1 plus 10.21 format. So we're going to have to then take our inputs, components, IO, inputs, and we're going to have a few inputs. And we're also going to need to grab our components, custom, and our 1024 by 768, just like that. Okay, so what we're going to do is I guess we'll call the top X and the bottom Y, just because it's easy like that. So I want to align that real nice. Yeah, that's how we'll do it. Perfect. Okay, so we'll call this zoom factor. Zoom factor, and it's going to be 32 bits. We're going to drag that up, connect it in there. So what we're doing is we're doing our zoom factor times then x and y. All right. Okay. But this isn't going to work because remember what I said? I said this is our 1.10.21 format, and our zoom factor is just going to be an integer. Like, actually no, never mind. I lied. The zoom factor is fine. Zoom factor is fine. It's the x and y. The x and y are just the integers. Zoom factor is a 32-bit 1 plus 10.21 format. These are just the 10 part. So what do we need to do? We need to grab components, wires, and splitters. And we need to take in our 10-bit number and we need to output the 32-bit number. But the way we want to do this is we want to output a single 32-bit number, and we want our inputs to be 1, 10, 21, like that. Okay, beautiful. So then we'll take 2 of these, and now the 0, the most significant bit here is going to be a 0 because it's positive. So we'll tie those together. We'll take this one in. Those 10 bits in, we'll take these 10 bits in, and then we could take this here. Well, I guess for neatness, we'll do it like that, and we'll pull that low too. So now we're going to go to components, wires, ground. This is just like the easiest to use in my opinion. Boom, like that. So we're tying the most significant bit of each 21-bit number of each 32-bit number low, because we're just using the 10 bits below that as the integer. And then we can pass that in like that. Beautiful. Alright, one last thing. I'm going to pull that back just slightly, so if I need this overflow, I can get to it. Okay, so now we're going to need a clock. And instead of doing that, what you do is you just grab components, IO clock input. You just grab the clock like that. And then that automatically puts that little triangle symbol in there. We're going to need our real bound and our imaginary bound. It's going to be 32 bits, of course. Oh, whoops. 32. Whoops. 32. Imaginary. I'll just call this inbound. Okay, So now we're going to take, now if this is the axis, this is the reals, we're going to take the output of that plus the output of this, and then we're going to take that plus that. And now if we go to components, arithmetic, adder, oh, I can actually do, oops, I can actually move down like that. Control C, Control V. We're going to tie the carry in low like that, and then out here is going to be the real and the imaginary. Or it's just going to be real and imaginary, not bound. Where it's not the bound. We're actually generating the real and imaginary outputs based off the bound and the current zoom factor and the XY coordinates. So we will go to components, IO, output, make them 32 bits. We will call that the real, imaginaries, I don't know, ims, I guess. Yeah, and there's a few more things we gotta do still. Okay, yeah, so the last few things we gotta do is we're just gonna pull the overflow out like this. It's a single bit. We're just gonna call it OVF. We need then Control C, Control V, a clear, which is a single bit. And an enable. I don't want capital. Okay, and that's, oh no, and one last thing that we need still. Sorry. I'm gonna pull Y out like that. I'm gonna pull X out like that. I'm gonna call this X, and it's a 10-bit number because it's before the splitter. I'll call that Y. Okay, now there's the full circuit right there. So now this will generate our mappings. And that's basically it for this tutorial. We can run it and see what works. Oh, this has to be 21 bits. And that needs to be 1 bit. There we go. And then there's 1 bits needed, but 32 bits found. That's because this needs to be set for 32 bits, and so does this. And now it should be good to go. So, yeah, so if we put in our real bound, let's do -2, -1.5. So the real bound is going to be FFC, and then the imaginary is going to be FFD. So let's just type in FFC and then a bunch of zeros until it gets perfect. And then this one is going to be FFD. FFD, there we go. Okay, so there's our real and imaginary bounds. Oh shit, we're gonna have to clock this by hand, that sucks. So if I set my zoom factor for being like 1/256, which would be like, if I pull up my Windows calculator, 1 divided by 256 is equal to that. It's 2000. Apply. Okay. And then now it would literally take, once I enable this, now as I clock through this here, let's see what's going on. Why is nothing coming out here? 9. Oh. Yeah, we gotta investigate this. Well guys, it goes to say that I'm really dumb. So first off, what you have to do first is name this like CLK for clock and give that name. Come over here and then reverse this. Go 21, 10, 1 like that. 21, 10, 1. There you go. There we go. And then we're going to change that to being 21 bits. We're going to change that to being 1 bit. And now hopefully, if we were to put in FFC 0000, whoops, and put in 2000 here. And I changed the clock to being at 1 Hz real time. So now if we enable this as X increments, the reals increment. That's exactly what we want. So now the circuit is mapping the X addresses to the reals, and as it changes the X, you see the new real. And then once X gets all the way done and overflows, it'll increment to Y by 1 and then continue through all the X's again. So now you can see how we're scanning across the plane, generating all the values. These are the values, the reals and imaginaries, that will be fed into our math unit that we will work on in the next tutorial. But for now, we have generated the base thing that will allow us to draw a Mandelbrot frame anywhere we want, just by changing the bound, and then we can zoom as much as we want by changing the zoom factor. So we have to then add like a circuit before that would take care of the zoom and pan. That would allow you to just press buttons to do that, or the user could just manually enter some stuff for now. So that's why we're just after this going to move on to getting the math working, so then you can actually plot it. And yeah, if you guys made it this far, thanks for watching, and I hope you guys subscribe, and I'll see you guys next time. Take it easy.